My name's Tom Wilkie. I'm a software engineer at Weaveworks. Hopefully, so I'm going to try and move quite quickly through this talk because I've got 3 demos to do. So if I'm going too quickly, just shout. Like, interaction during the talk is really, really good. Like, feel free to interrupt me. And if I miss a hand up, just shout out. And on that note, who here is kind of more of an application developer than infrastructure? Okay, and I guess everyone else is infrastructure? Who's infrastructure? So who didn't put their hand up? You're infrastructure. Well, I suppose you're kind of... Okay, so I guess there's ops as well and kind of DevOpsy stuff. Okay, who's running Kubernetes in production? Okay, who's running Weave? I think there was a hand up over here. Or are you just exercising? Okay, that's cool. That's good. Great. So monitoring microservices for Kubernetes, interactive monitoring. The talk's had many names. I'd like to break it down into 3 things. This is monitoring, visualization, and tracing. And I'm going to go through. The talk's going to be split into 3 sections, hopefully 10 minutes each. And really the whole thesis of this talk is I want to persuade you that monitoring for microservices is more than just drawing pretty graphs with time series data, and that really you need to care about these 2 other topics, visualization and tracing, and you need to use these new techniques in your microservices-based application. So this is mainly going to be focused more on the application developers, but maybe these techniques could also be useful for infrastructure guys. So, monitoring. Well, you should all know, most people, when you say monitoring, they think time series data. They think drawing a nice chart, seeing historical trends in your data. How does this change when you start talking about microservices? And I'm really talking about microservices because I think Kubernetes is a platform that encourages you to write in this microservice-y way. And what do I mean by microservice-y? I like that word, service-y. What do I mean? Well, I mean this kind of model of, well, here we go. I've got a slide, actually. So this is your traditional. You've probably seen this at the beginning of every single talk this past 2 days. One of the things I think is interesting about this conference is we've got a real kind of bifurcation of people who are really early, don't really know what microservices, what Kubernetes is, and we've got some guys who are really kind of in the thick of it, doing everything, know exactly what this is. So I'm going to try and rattle through, kind of the motivation for this. And if I lose you, just say. Yeah, traditional application architecture, everyone should be familiar with this. You've got a big monolith in the middle, maybe some replicated database at the bottom, some load balancers at the top. Obviously, hugely simplified. What are some of the characteristics of this, with respect to monitoring? Well, it doesn't change very often. You might find that, each of these little blobs, we call them fried eggs, because they kind of look like fried eggs. Each of these little fried eggs probably has its own machine, or maybe its own VM. And yeah, there's just a small number of things to think about. And it's generally quite straightforward. Whereas in the microservices architecture, obviously this is not a microservices architecture, because you can't really define what a microservices architecture is. Generally, I think of this as a microservices architecture, and Kubernetes is more of a kind of a change in the contract between developers and the people they work for. There's kind of this shift in responsibility for the architecture. And that developers are being given way more authority to make their own decisions, to choose their own tools, to choose their own languages, their own technologies. And generally this means your architecture is much more organic, much more kind of, what's the right word? Much more kind of evolved than designed. If you're an architect, this might be bad news for you, but hopefully it's not. So there's no prescribed topology. It changes all the time. There's a lot more moving parts. You might find each of these blobs has, tens, hundreds of replicas. And also kind of I suppose the whole thesis for this section of the talk is that the primary key for monitoring is changing. The primary key for monitoring used to be machine. Oh, I've jumped ahead of myself. I'm going to hold that thought about primary keys. Just to reinforce the point I was making, this is the old world, arbitrary picture of cats. Everyone has to have a picture of a cat in their talk. But you've probably heard this saying 100 times, it's so last year, and it's getting really old, but I'm going to say it anyway, which is you should treat your system like cattle, not like pets. Right? And what does this mean? Well, what this means is, in the old way, you tended for your applications, you tended for your load balancer, you tended for your monolith. If it got sick, you tried to find out why, you maybe, tried to fix it, I don't know. You cared a lot for it. And whereas in the new world, in the microservices world, you've got these set of replicas, all of which serve a particular service. And if one of them starts saying, I'm not healthy, Kubernetes is just going to automatically kill it for you. That was the keynote yesterday. You're just going to kill it, and we're just going to start another one. So the idea here is that farmers apparently kill their cattle when they're ill, which just doesn't work. But yeah, and the idea here is you should not care about the individual process. You care more about the service as a whole. What did this is an old world. This is not one of mine. This is something I pulled off the internet. But this is what monitoring used to look like. We've got some disk I/O, some CPU usage, some memory usage over there, look. And this is what you would look at. And you would try and infer what's happening to the application. The primary key here, as I was saying, is the host. Really, we're looking at the resource usage for a given host, or maybe a collection of hosts. And this is a model. Brendan Gregg, great guy, really clever, got some great ideas. This is a model he purports, which is the use method. For every resource in your cluster on your machine, you should think about the utilization, the saturation, and the error rate for that given resource. If you've not heard of this, you should have really. It is something you should think about. And this is definitely important. One of the nice things I like is it's very simple to understand. It's very kind of a checklist. If something's gone wrong, I'm going to go and look at these things. If I'm building a monitoring system, I'm going to go and look at these things. But I think this is wrong. Or at least I don't think this is sufficient. He got very upset when I said it was wrong, so I should say it's just not sufficient. And I think we really need this new method, invented by me, trademark. Not really. This is a bit tongue-in-cheek. I don't like acronyms. But I think for every service in your system, you need to be measuring things like the error rate, the request rate, and the latencies. I put duration because red is much better than rel. But yeah, you should be taking a much more service-oriented approach. And you should be thinking about your primary key should be service. When you look at a monitoring dashboard, it should be visualizations and graphs of the service characteristics, not the host characteristics. Because at the end of the day, in this new microservice architecture on Kubernetes, this is what you care about. You want to know if one of your services is serving errors. You want to know if one of your services is taking a long time to serve requests. So yeah. This is how you do it, right? This is horrible. I hate putting code on slides. But generally, this is using Prometheus. This is some code copied out of the service that we run at Weaveworks. And we set up a metric. This is RPC latencies. And we register it with Prometheus. And every single HTTP request, we record the latency. And we thought a while back, there must be a better way of doing this. Because this kind of needs, I talked a little bit about this shift in responsibility when architecting a microservices-based app. This needs every single individual developer or team of developers to buy into this method. You need to go and instrument every single service in your architecture. And that's hard to do. In the new world where you've got to persuade everyone because there's no kind of central authority on architecture, this might take a while. And wouldn't it be nice if this didn't need to be done? Wouldn't it be nice if you could just automatically get these metrics from your infrastructure? And, before that thought, this is what it looks like. This is an actual dashboard of a dev cluster for the service that we run at Acunu. And this is exactly that. This is those metrics that I showed you. You look, this is the app mapper is one of our services. The user service is the thing that stores the passwords. This is indexed by service. I don't know where any of these are running. I don't know what machine they're running on. I'm just looking at the QPS for the service. So there must be a better way. And we think there is. If you're following Kubernetes best practices, you're deploying your services using the kube proxy. That's how you balance traffic amongst replicas of your service. So there's already this thing in the middle that sees all the traffic. So why not instrument that instead? Why not gather your metrics there so your developers don't have to gather their metrics, instrument their code? And yeah, we think we think there's some legs in this idea. So we built a little prototype, a little alpha load balancer, and we put it out there. And I'm going to give you a demo of it. So, I hope the demo gods are smiling on me today. I have tried this a few times. If it doesn't work, we can blame the people that wrote this software because it wasn't me. Let's see. Can everyone read that? Yeah, this is good. I'm not seeing any people saying this is, yeah, okay, it's good. So we need to, I'm just going to show that there's nothing up my sleeve. Oh, there's loads of stuff up my sleeve. Okay, I'm going to delete all of that. Live typing. I'm not sure this is a good idea. Now I'm going to go to my pre-canned list of commands I need to run and run those. So this demo is not quite as slick as the rest of them, purely because this is so early, this software. I don't think we've ever actually demoed it in front of a live audience like this. So bear with me. So we've just started this thing called Flux. This is our instrumented programmable load balancer. It's made of a bunch of different containers doing a whole bunch of different things. It uses etcd to coordinate state. And we've just started it. So let's just tell my environment where etcd is. And you can see we've got this thing called Flux Cuttle, a bit like kubectl. And we can see what it knows, and it doesn't know anything. So then we will register a service with it. And we'll tell that service to route traffic to certain containers. And it does this kind of like Kubernetes labels. How do you do that? Select. There we go. And now if you do that info again, you see it knows about a service, but it doesn't have any instances to route it to. So let's run a couple. Oh no, let's run a couple of instances of our Hello World server. This is particularly advanced software, and hopefully we should be able to. Yeah, of course, yeah. All of this is online, by the way. This is all open source. So there's a tutorial on how to do this online if you get stuck with the individual commands. But let's see what we're doing. I have to go to a particular port. Oh, yes. No, I have to run an external Nginx, which Flux will also configure. And then I go to port 8080. And I see a load-balanced Hello World. So every time I refresh, I get a different host. There's 3 of them. So that's pretty straightforward, right? Nothing clever there. You can easily do this with Kubernetes and kubeproxy. But one of the things I quite like, let's just run that curl example. So this is just putting some load on the system. This is curling it, sleeping for 100 milliseconds. So we should expect about 10 QPS from this. And hopefully I can show you those QPS actually coming through. Oh, I have to remember what port we put this on. 7070, for those who are paying attention. Here we go. So this is the Flux dashboard. Along the top, we've got some services. I've only got one service. And then we've got various different ways of slicing and dicing the stats it's collecting. All of these stats are being put into a Prometheus in the background. So this is not some black magic or anything. This is just Prometheus, but it's the instrumented load balancer that's collecting this data. So we can see some graphs. This is broken down by instance. We could see it broken down by, this is just broken down by image, because that's how we selected the ones to load balance here. And you can see it's getting about 10 QPS. So this is this is more of a proof of concept of instrumenting the load balancer should actually kind of work. And if we kill the curl, hopefully you'll see it actually report 0. It's only collecting on a 5-second window. So there you go, 0. Yay! So that's the first demo. We Flux. Yep, still working. Good. Yes. So the demo kind of goes on, but I've got to fit 3 into the whole talk. So there's a demo about how you can then run another service and programmatically move like 10% of the traffic to that service, and then see the error rates side by side with those 2 services. That's the one I really wanted to give, but I had to cut it. So anyway, that's Flux. It's on GitHub. It's all open source. It's written in Go. It runs as a Docker container. You can try it out and play with it if you like. Moving on. That's monitoring. The thesis here... Oh, I've lost my speaker notes. Bear with me a sec. The thesis here is really that when you're doing monitoring for microservices, you very much need to think about your primary key being service and not being host. There we go. That's the thesis. Hopefully, no, that's not too contentious. Do people think that's a good idea? It's not really a new idea. Anyway, next one, visualization. This is really where we come into my stride because this is the thing I work on. The whole thesis of the talk is that you need to do things other than just time series monitoring when you're monitoring your microservices. And really I want to talk about visualization. and how we can use, a good visualization tool to help us really understand what the service is doing and help us maybe onboard and train new members. And generally, if we just use this concept of this architecture diagram of the service to kind of key all our interactions with the service, hopefully this will kind of make monitoring these systems, managing these systems that are now much bigger, an order of magnitude bigger, much easier. So how many people here have drawn an architecture diagram on a whiteboard? Yeah, most of us, right? Okay. And how many times when you've drawn it has it been wrong? Most of us. Yeah. So I've done this plenty of times. When I was trained at my last job, it turned out everything they taught me was wrong because it all moved, it all changed. And it turns out it's not good enough to draw it on a whiteboard, take a picture, stick it on a wiki. Because as I said at the beginning, these architectures are much more dynamic. They're changing all the time. Don't take photos of that. So this is the thing I work on. I spend my time on. It's open source as well. It's all written in Go, runs as a Docker container. It's called Weavescope. Anyone who was in Albin's talk earlier might have saw a quick demo of it because he used it to demo his latency injecting thing. But the idea here is that we scrape the system. This is not declarative. This is all live and real data. And we go and scrape the system. We talk to every single interface we can. And we gather this information and kind of munge it together until you get this kind of renderable, pretty graph of exactly what's going on. So this is just a demo app I've written. The other thing you can do that's quite nice, if you select one of these nodes, you get a kind of zoomed in view and metrics and kind of relationships saying this is what's inside this container. It's quite similar to the Sysdig stuff. The nice thing about this, is anyone from Sysdig here? No? Oh, I came to your talk. Yeah, the nice thing about this is it doesn't require a kernel module. But the challenge with this, when you're running on a vanilla kernel, is how do you kind of find out who's talking to whom? How do you find these edges? And what technologies can we use to reliably and predictably find the real edges? And this turns out to be a real problem. Some more code. This is more just to kind of show you that there's a lot of information. If you're doing this without a nice graphical tool, you'd have to run contract, or you'd have to cat procnet TCP, and you'd have to kind of interpret what is this that I'm showing you. Well, these are kind of indexed by IP address and source and destination port, and these things here, helpfully, are indexed by inode number. So everyone knows their inode numbers, right? So if you're using these procnet TCP data, not only do you have to go and be really careful about exactly what network namespace you're running in. With containers, turns out if you run this in the host namespace, you don't see all the connections. But you also need to go and walk the proc file system and find all the inodes for particular sets of processes and then map them back. And there's no kind of consistent and atomic way of getting both pieces of information, so it kind of gets out of sync if you're not careful. And the way I like to think about this is that's the laser pointer, is a Venn diagram. Everyone loves a good Venn diagram. This is all the connections that actually exist in the real world. And we want that set. And we've got these techniques to get that set. And it turns out if you just walk proc, you get this small subset of connections. And this is because reading the proc file system is kind of expensive, especially if you've got lots of connections. You have to poll it. You have to walk it every few seconds. If you do it too often, your monitoring takes over and is using all your CPU. This was a problem we actually had in Scope. And so it turns out you walk it infrequently. You've got this challenge that I was saying about the consistency between walking the PIDs and walking the proc net. And so you get this subset of usable connections. But it's kind of good because you know the process for each connection. And then you can use the process to find the container, and you can use that to find the pod. And so you can build up quite a nice little graph. But it's not enough because you're going to miss every short-lived connection. If you're only walking this every 3 seconds, any connection that takes less than 3 seconds, which is probably most connections coming into your front end, is going to get lost. So you've got this other thing. You've got this thing called contract. This is a module in the kernel that is involved in that. I'm not a kernel engineer. But there's an interface, and you can get this interface, and it gives you real-time events of who's speaking to whom. But this time it's keyed by IP address. So you can't identify the individual process, but you can identify, say, the container, except for if the container's sharing a network namespace, like with Kubernetes. So you get kind of a different subset. It's not really a subset, it's kind of overlapping because you also get a bunch of data that's not quite right. We're still working on that. One of the things I was looking at this morning. And then we've got this other thing. This is kind of really interesting when you start thinking about Kubernetes and Flux, the thing I mentioned earlier. you've got these things, these load balance connections, where the real connection is going to a load balancer, and then the load balancer is maybe sending the next connection on, or where that connection's being forwarded by IP tables. And these connections, well, you kind of maybe don't want to show everything talking to a load balancer, because that's not really the architecture of your application. You maybe really want to show, you want to remove the load balancer from that situation, but it's not obvious how to do that. Load balancers aren't instrumented to do that yet. This is something I was working on a few days ago. So yeah, you've got these different sets. Right now, Scope gets the stuff from proc, gets the stuff from contract. We're working on eBPFs, which are these filters you can inject into the kernel, that will little programs you can run and will give you more information. Hopefully that will give us the whole set, minus the load balance connections. Hopefully with the I love this laser pointer. Hopefully with the load balance connections, we can instrument things like kubeproxy, and we can instrument Flux, and hopefully this will integrate that with Scope, and we'll get more information, but this is a challenging problem. So, demo time. Demo number 2. I'm currently on time. So, bear with me a sec. It's really annoying how you have to switch screens. Go away. So, let's try a different tab this time. Hopefully this one will work. Oh, another tab. So, a bit bigger. Clear. Great. So, let's delete everything again. Live typing in a demo is always a good idea. Luckily, not much typing for this one. So we've deleted everything. The example app I'm going to use uses our network called Weave. I'm not here to actually talk about that, so I'm just going to say we have an SDN. It is now running. There's some containers that run the SDN. And then we're going to go to this example application. And this example application is the one that I showed you in the slides earlier. The idea here is it just gives us something to show. It doesn't actually do much, but it kind of combines a whole bunch of Java, some Elasticsearch, some Python, some Go, bunch of C. It's got Redis in there. It's got, it's a mix and match of everything, and it's just designed to paint a pretty picture and spew errors on the logs. And then this is kind of obvious, right? Everyone looking at that knows exactly the architecture of the system I've just spun up. Yeah, okay. Maybe less sarcasm. But of course, this is the problem Scope's designed to solve. And if we do a Scope launch, it runs a container and it tells you can go and connect to that URL. So, Scope URL. There we go. This is a live system now running on a Docker machine on my laptop. This is exactly the one that I showed you in the graphs. And here you can see things like CPU usage, memory usage. You can see the information the container was started with. You can see the processes contained inside the container. One of the nice things I like about Scope is it's way more than just a visualization system. We've got these, Alban was showing these earlier in his talk, these controls. So we can start and stop containers. We can view the logs for a container. This is a JavaScript VT100 emulator that everyone seems to use, and some WebSocket plumbing in the back end to connect this to a Docker attach. We can also get a terminal inside the container. This is just a container that I've Docker exec'd into and then used a set of WebSockets to connect up. The idea here is that if everyone understands the architecture of the application, then if we allow both operations and applications developers and maybe infrastructure guys to use the same concepts and use the same structure to interact with the application, maybe this will make communication between these different guys the same or easier. One of the nice things you can see processes, there's a very abstract graph data model behind this that's just nodes and edges. And we have various ways of aggregating together these nodes, and when you view processes, you can aggregate them by name, get a different view for the system. You can view containers. You can group these containers by the container's DNS name. And this, in my view, is the kind of diagram I would draw on a whiteboard if I was trying to explain the application I'd just built to one of my engineers. You can also group them by image. This is another great proxy for service if you don't have real services like Kubernetes does. I didn't bring up a Kubernetes example, so I can't show you, but we have views for pods and services as well. This hosts one's quite interesting. It shows you, this is one of the problems with connection tracking. This is showing you actually the fact that it can't see the other end of these connections to decide what host they're on. But this is quite nice. It gives you all the containers sorted by CPU. It gives you all the processes. You can sort by CPU or memory or process ID. Why would you want to do that? All the container images. This is the kind of thing. There's another aspect which you can navigate. Scope understands the links between the different objects in the different levels of its hierarchy. So you can navigate to, say, the Weavescope container, and you can navigate to the Weave container from there, or maybe back to the host again. We've got an excellent UI guy who's done all of this. But this is Weavescope. This is the visualization product we've built. It's all open source. It's all written in Go. Hopefully people will find it interesting. The direction we're probably taking this in is integrating it more with things like Flux, so you can see those statistics that I showed you there in this UI. We've got some really nice stuff lined up for the next release, where we can paint individual nodes with different fills depending on different metrics, CPU, memory, and so on. So that's Weavescope. That's the second demo, and it worked, which is the main thing. So let's switch the display back. Okay, so that was Weavescope. There's a whole bunch of different URLs here, but you can see that for yourself. This one is the GitHub page. This one, we have a Slack channel if you want to connect to and come and talk to me or any of the other guys at Weaveworks. We also run Scope as a service online. So Scope's architecture is split in two. And if you run it online, you get some features like being able to share URLs and things like this. But this is very early days. We're still kind of working on that and trying to decide exactly what features are going to be there and our product website. But yeah, come and talk to me on Slack. That's how I met Alban. I'm going to keep referring to you because I'm so glad that you demoed Scope in your own talk. 0.13 came out 2 weeks ago. We're trying to keep quite a high cadence of releases. We're trying to do a release every kind of 2 to 3 weeks. That means if you've got something really urgent you want to see, or you submit a PR to us, hopefully, it won't be long before you get that into the real world. So, this is something I want to show you. What does this look like when you run it with Kubernetes? So as I mentioned, we use Kubernetes to run our service. You can't see that. And I wanted to show you a live scope on Kubernetes and kind of talk about some of the challenges there. Okay, so let's go to the service. Let's connect to the production cluster. What could possibly go wrong? There we go. This is just a little SOX proxy that I wrote that gets you into the cluster. And then you just tell your browser to use that SOX proxy, which has been SSH port forwarded to your local machine. And now you're on your cluster network and you can talk to anything within your cluster. And I have to remember the URL. And this is running, I think this is production. Now the big challenge here, this is the one thing I think is really interesting about Kubernetes. I said about those load balanced connections, about how you just see everything going to and from a given, a single process. Well, that's what we're seeing here. When we see this uncontained process, these have, one of these is the kubelet, one of these is the kube proxy. And you end up with something that looks a bit skewed and you don't really get the real architecture of your application. And this is something we're working on, and it's a bit of a shame. You probably saw the flyers which had exactly this screenshot. The other thing we want to do is we want to start mapping through some of the controls, some of the terminals that you get and the features you get from Kubernetes into this view. But here's the kind of pods and services view that we've built for Kubernetes. Yeah, so that's what it looks like when run on a Kubernetes container. I do actually have a slide which shows much better the problem I was describing. This is the problem I was describing. Look, this is a hypercube cluster, and in here, this is the proxy you can run. Every single process is talking to or being talked to by the proxy. That's the problem we really want to avoid, and we really want to kind of come and instrument the kube proxy so that it exposes, the actual kind of which incoming connection is connected to which outgoing connection. So, hopefully kind of the impression you're getting is this is all very much a work in progress, and we really want your input and feedback on this. Right then. So the conclusion here, hopefully I've given you a bit of food for thought about maybe we should be using visualization tools to understand our architecture instead of asking people to explain it on a whiteboard. That's really the conclusion I hope you'll get from this section. So final bit, tracing. So if the last two things were kind of, alpha and then beta, then this one is very much a proof of concept. 10 minutes, okay. This one is very much a proof of concept. This is a pet project of mine. I used to work at Google and we had this fantastic tool called Dapper. And when I moved into the open source world, I was kind of really disappointed to see that things like Dapper weren't more widely adopted. So what is distributed tracing? Everyone's familiar with this, I hope. This is a Go PDF of the profiler. And this is really useful when you've got a single binary or a single process. You can see where time is being spent. You can see if it's the GC or if it's whatever it is that's causing the problems, and you can go and fix that. But when you move into the world of a microservice distributed application, this is not enough. You want to see this for every process, maybe joined together with the connections linked, maybe on a per request basis. And this is what distributed tracing is. Hopefully, this isn't new, and you should all know what distributed tracing is. This is Zipkin, a project by Twitter. And they have a fantastic UI and fantastic instrumentation for all of their, for all different languages, so that you can get these kind of views. As I said, not a new topic. The paper I particularly like is the Magpie paper by Microsoft Research. And they talk about a way in which maybe you can do this problem without instrumenting your binaries. Maybe you can get enough information from the OS. And this got me thinking, could we do this on Linux? Obviously, this was done on Windows. And Dapper requires you to instrument your application. Maybe there's a way of doing this that doesn't require you to instrument your application. So what's the problem here? Why do you have to instrument your application? Well, the problem is, for every incoming request to your given process, you need to figure out what outgoing requests got made on behalf of the incoming request. What's the causality going on here? And this is a black box. So the way, as I said, the way we do this with Dapper, with things like open tracing, is we propagate some unique ID. Maybe we stick it in a HTTP header saying, this is request number 123. And then on every outgoing request, we propagate the same unique ID. But of course, to do that, you need to go and make sure your application does that. That means you need to instrument your application. So this means you need to modify it. And again, this comes back to the same problem I was talking about earlier. We've got this change in the way we organize our teams. So every different team is responsible for their own service. But this is kind of a global thing that requires a mandate from on high, which everyone hates. So what you'll get is you'll get some teams that just don't do this. Maybe it's not important to them, maybe you haven't persuaded them, but some teams won't do it. Maybe some binaries are unmaintained and there is no team to go and instrument that binary. And then you'll see your traces just stop whenever they hit that binary. And because you're not propagating the ID through the binary, you don't get the full trace. So we thought, I thought, wouldn't this be awesome if we could do this without application modifications? Wouldn't that be nice? And then for those cases where you can't persuade the team to instrument their binary, you maybe have some other techniques. And I think you can. You can intercept these system calls. This is kind of what the Magpie paper was saying. Intercept these system calls. Use this data feed you've got now to build up a little data model of which threads in your process are reading and writing from which file descriptors. Which file descriptors are talking to what IP and what port. And basically build this little model of which connection caused which other connection. Using a couple of heuristics. Maybe it's not 100% perfect. I'm not claiming this is going to replace every single system, but it actually turns out to work reasonably well. So another demo. This is the last one, I promise. And this is the one that's most likely to go wrong. So let's kill that. Let's make sure we're not talking to that proxy anymore. That's my email. Don't look at that. Direct. Okay, so I've got another tab up here. Tracer. Bigger font. As with every demo, we're just going to delete everything again. Get really used to typing this. Right then, so we're going to run the example. We're going to run a different example, slightly simpler, because this really is early days for this piece of software. This time it's just going to run 3 containers. We'll go and run scope again so you can see the architecture of the application I'm going to trace. 192. So, just give it a second. This is where you're supposed to see some lines when they start communicating. And this is where we find that they name was... okay, I know what I did wrong. Let's try that again. I forgot to run Weave, and it's using Weave DNS to talk to each other, to find each other. So let's run Weave. Now let's run that example again. And now let's run scope. And this time we should see the thing talk to each other. There we go, yes. Sorry, get excited. So we've got a client application. This is just a little load generator. It's curl in a for loop. This application is doing something very simple. It's talking to a quote of the day server, which is going to the internet and getting me a quote. And then it's taking that quote and it's giving to an echo server. And this echo server is going to capitalize the quote. This is complicated stuff. But I want to see why this is slow. You know, our users complain that this thing's slow. So, tracer launch. And the tracer is now running on port 60. Okay, we're running out of time, so I'm going to rush through this bit. But basically, we can start tracing the given application, and we start seeing some requests coming in. So I've throttled this right back, so we don't see too many requests. But if we go and look at this request here, that's a bad example. We're going to look at this request here. We see that there's a request going to some application, and another request going to a second application, and that one's taking really long. Now, this has all been done without instrumenting that app, that little Python app I wrote. So we've managed to already infer that causality I was talking about. But clearly that's not enough, because I don't know what these requests are doing. So maybe I go and start tracing a couple of more applications, the quote of the day and the echo server. And then, fingers crossed, we see them being joined. We see this one saying, well, you're talking to the quote of the day server, and that's also doing another request out to the internet. Turns out the internet connection here is pretty good. And you can see this one, hopefully, will be joined, and this will start saying echo. So it's the echo server is the second one we're talking to. And if we pick one of the long connections, we can see it's the echo server that's taking a really long time to capitalize those characters. Maybe that's where I should go and look. And this was all done, this whole demo, this was all done without instrumenting any of the binaries. So, as the host will be very pleased to hear, that was pretty much the end of my talk. Tracer is also open source. It's in the experimental directory of Scope. And of course, that URL is wrong. So go and look at Weaveworks Scope Experimental. That's tracing. Hopefully, I've kind of tried to persuade you. I've got another slide at the end with all the links on. But that's Weavetracer. Any more pictures? And then tracing. So hopefully, I've tried to persuade you that you really want to do some distributed tracing when you're using microservices, when you're using Kubernetes. You know, there's another challenge here, right, which would be instrumenting the kube proxy to propagate these connections and being able to detect them from that. And really, when you're doing monitoring for microservices and for Kubernetes, you want to think about all of these things and not just time series data. Any questions? And there's those URLs. Thank you.
I think we've got time for one question. If there's, I did see that hand go up pretty fast. So.
Is there any way to get data into Scope if you were using a tracing tool inside your application? So without your other tools, I guess.
So the question was, is there any... Oh, you've got a mic, so the recording knows what the question is. Scope's not really about tracing so far. That's really a separate function. Maybe one day we'll build the tracer into Scope. We don't know yet. But Scope does have a plugin mechanism, which we're just building right now, a chap called Paul's building. And very much the idea is if you know a bit more about the topology of your application, or maybe you're running on EC2 and we can write an EC2 plugin which goes and scrapes information about the environment you're in, appropriately annotates the nodes, gives you little URLs to click to get to the EC2 dashboards. Yes, very much. We want this to be an open thing. And similarly with Tracer, if I had time to work on it, I would see this as being complementary to the existing Dapper and open tracing techniques for propagating IDs. And so very much, yes, I want this information to be exchanged between these two kinds of systems. Thank you.
Cool. I think we're out of time, guys. But you ran this afternoon, Tom, for a chat?
I am going to the pub after this, so the longer you talk to me, the longer I stay.
Find Tom in the pub. Cool. Thanks once again, Tom.
Thank you very much.